So one last thing to talk about with binary code this week. And I left this up here while I was racing the board to make this point, right? We've talked about numbers, lots and lots about numbers, but that's not our only type of data, right? The traditional data, we've already talked about strings, the traditional way humans have stored data. That's actually how we define the line between prehistory and history when we develop written word. So really, most of our data is we probably want to store it this way with our written language. So we need a way to do that in binary code because the machine only works with binary code. And it's kind of like what we did here with those error correcting codes, right? In that example, I wrote down to 6, or the code word, I wrote down a bunch of bits, wrote down 7, there were 7 bits there and just said, that means 6. Which in essence is really what we did with all that math stuff in the previous lecture, is we just had the symbols there and we said, okay, this column means this and that column means that. We just defined it ourselves. So we're going to do the same thing for our written language. So our book just talked about ASCII code. That was the sort of the originator. We're in our symbols, right? Works great for America. That stands for America. The A there stands for America. It's in the textbook, the whole thing. But works great for English. But English isn't the only language in the world, right? There are a lot more symbols. So might as well put in Unicode here. So UTF-8. That's whenever you want you say Unicode, but if you're typing in what language you want, what encoding scheme you want in the computer, you're going to say UTF-8 for Unicode, which is just more ASCII extended. So we didn't start over from scratch, right? So ASCII is 1 byte. So we'll use 1 byte to represent a letter. In ASCII. So 1 byte means we have 255 symbols beginning with all. 256 values. With our numbers, it was 0 to 255. But we want our letters now. So we'll just go ahead and say 256 values. So, and then Unicode is because English isn't the only language in the world, right? We're going to do European languages and Asian languages, East Asian languages, Central Asian languages, Arabic languages. We're going to get way past 256 symbols pretty quick. So that's what Unicode is. It's just an extension on it. The first 256 values in Unicode are ASCII code. So it's just an extension on that. I guess I could erase this. The book only mentions ASCII code. The homework questions are going to say ASCII, so we use Unicode anymore. But the first 256 values of Unicode are ASCII code. And we just extended it. We didn't start over from scratch. So we can store 256 values in 1 byte of data. And just like we did, it was a little clearer with that error correcting code where I just wrote down some 1s and 0s and it's like, okay, this means 6. Well, we can do the same thing to represent our letters, right? We're going to say, okay, we need something to represent a capital A. So let's use 65. And then we need to translate that to binary. 1, 2, 3, 4, 5, 6, 7, 8, which we've done a few times. So in 1 byte, our first bit here is going to be 2 to the 7th, 128. So we don't have any of those at 65. Cut that in half. Our next bit is 64. Oh, we got one of those. 65 plus 65 minus 64 means we have one left. Then we have a whole bunch of zeros. So that is how we will represent a capital A. And then a question that I like to often phrase when, like hours in the Student Success Center here at school, and tutoring people on this, because it almost always shows up. How many letters are in the alphabet? Say 26. That's what we've learned since we were in elementary school, right? So a human is 26, but really we have 52 symbols. Because a capital A is not the same thing, as a lowercase a. So those are different symbols. So we don't want to represent both A's with the same code. Because, well, humans can handle that no problem, right? But humans are intelligent. Machines are not. So we need a different code for our lowercase a. So let's say 97 means lowercase a. And we just want it in binary. 1, 2, 3, 4, 5, 6, 7, 8. So we don't have any 128s. 64, we'll have one of those. 64 plus 32 would be 96, so we'll have one of those. Oh, and we're only one left of this, so then we can hit zeros all the way over and we get the ones. So a 97 represents a lowercase a. So that's our encoding scheme to store written data. So in the textbook, on page 735, Appendix B is where the chart of ASCII code starts. 1, 2, 3. So 3 pages worth. There are some other symbols that you might want to include. You could write them on a piece of paper, or there's no shortage of the full chart online of ASCII or the full Unicode chart. And ASCII is the first 256 values in Unicode. So you can just find a big Unicode chart you like the formatting on and keep that around for future reference. But we can just use any of our numbers to represent any of our symbols. So the digit 0 is going to be a 48. And a space, I'm going to write it like that. Some of y'all will see that eventually. This is called an escape sequence. Sometimes we need certain codes to give a computer symbol. The escape sequence is things like, a backslash. A backslash means something when we're writing code in a computer. So if we actually want to type a backslash, we need a way to escape out of coding and say, actually, this symbol. So that's what a backslash is used for, an escape sequence. So if we actually want to type a backslash, we write 2 backslashes. You may have seen that one before, like copying addresses or file locations on hard drives, which are also still URLs, Uniform Resource Locators. But a backslash means something, so if we actually want to type it, we have to escape out of our code, put that symbol, and then come back to the code. So this is the escape symbol for a space, because there's not a good way to write a space. That'd be a 32. So obviously there are charts to refer to, but you might want to get a good feel for some of these. These 4 might be a good start. So capital A is 65, and then you can just count through the alphabet from there. Lowercase a is a 97, you can count through the alphabet from there. The digit 0 is a 48. So you're going to want to use ASCII code 0, because ASCII 0 is off. You're actually turning bits off in memory if you do 0 and 1. So you want to avoid that. And our first 32 values, 0 through 31, are control features. That's why the chart in Appendix B starts at 32. So that's things like 0 and 1 are on and off. 9 and 13 are useful ones to have there. Like line breaks, horizontal tabs. We have a vertical tab, but that never shows up. It's not even on keyboards anymore. We use the horizontal tab all the time. The one right above caps lock. Line breaks, carriage returns. Those are all, those are in the first 31 symbols, the control features. There's some beeps in there too. And then with ASCII 32, which if we put in binary, 32 is one of our powers of 2. That's 2 to the 5th, so 0, 1, 2, 3, 4, 5. So there's 1 there. Yeah. And everything else is going to be zeros. That's an easy one to convert. And yeah, we've gone over converting that. But we just use one of our numbers to represent our symbols. So maybe there's a couple you might want to try to commit to memory. These 4 basically, and then you can count from there. So space is 32, and then you can count through your punctuation on the top row, the ones above the numbers from the space bar, and then all the symbols above the numbers count from there. 0 comes in at 48, then 1's 49, 2's 50, and get your digits that way. Then lowercase a is 97, and capital A is 65, and you can count up through some letters that way. Or find a nice chart you like. There's lots and lots and lots of them, so really it just comes down to the formatting. Find one you personally like the formatting of. Because there's different ways charts can be made out, and there are some where they try to minimize the space the chart takes out and consolidate the information. It might be hard to read. If you come across some of those and would like to know how to read it because it fits nicely on an index card or something, let me know and I'll show you how to read those charts. But just find one you like the formatting of. And then this is our ASCII code. So a bunch of the homework questions, there's more about getting written word from binary code than there was about finding numbers. There's only a couple of the number ones. So there's quite a few about, here's a word, put it in binary, or here's a string of binary, figure out what word that's spelling. There's more of those in the homework. So let's go through an example of that. But basically we just pick a number to represent our symbol, and we already have a way to represent numbers. Is all there is to ASCII code, which is the first 256 values of Unicode. So I'll erase this and let's do an example. Now actually, some of you all may know a bunch of ASCII code already. The Alt keys, if you know that, that's ASCII code that you're typing in. If you don't know that, if you hold down the right Alt key and type the ASCII code, the decimal ASCII value of the ASCII code in the number pad, so the right Alt key and the number pad will put the symbol in. There's some software updates that automatically, and it'll allow you to use the left Alt key and the numbers up top. But the general format for that is the Alt key on the right-hand side and the number pad over to the side. You have to use those. So like in Microsoft Word, if you hold the right Alt key and type in ASCII code, you'll get a number. So I started to look this up for the example here, but then I stopped myself and was like, well, that's not how I remember it. Why don't I just show you what I remember? So I kind of remember sets of numbers, some sets that I use a lot. So like in my mind, I have this set of numbers, ones that are a little past what's in the chart on the book, for the ones I use most often. And that's going to be 176, 169, and 167. So I just remember that's the 3 ASCII code things I use most often. And I don't remember exactly which one each one is, but one of them is the section symbol. So from like legal, you've probably seen that in legal or government documents. IRS documents have the section symbol. So section, copyright, and degree. That's these three symbols. So I don't bother to memorize which one goes where. I just remember, like small sets of numbers, like these are the ones I'm going to use the most common. And there's only three things to try, so I just type one in, and if it's not that, I'll try again. It's only three things to try. But I think 169 is the degree. So, but whichever one it is, if you hold like in Microsoft Word, if you hold the Alt key on the right side of your keyboard and type 169 on the number pad, you'll get one of these symbols, whichever way they go. So if you're familiar with Alt keys, you already know a bunch of ASCII code. And if you've never seen that before, as you learn ASCII code, just be aware that you can type that right in instead of those big menus that you have to dig through really slow with your mouse. So there's that. So we need some sort of word that we can translate to ASCII code. This is module 2, so it's still going to be the month of August. Let's use that. So let's use the word August for our example. So in the classroom, every time I've taught this before, I would always go through this part by having you all tell me what numbers to write down, the decimal numbers, just to make sure everybody could read the chart before getting into the homework. Obviously, that's not going to work when I'm filming this video before the semester even starts. But if you have trouble reading the chart or find one that you kind of like the formatting of, you're not really sure, especially the ones that can fit on an index card in your wallet or something, they had to set it up a certain way to make it fit in such a small area. So if you have questions about the chart in the book or a chart you find that you think you might want to use, let me know. I'll show you how to read those. Because I can't really be in the classroom and have you all read off the chart to make sure everybody can read it. But the first step is we want to figure out the decimal value for each one of these. What number are we going to use to represent a capital A? We already saw that one, but what we do is go to our chart. The first page only goes down to 60. So the next page, there's a capital A, it's number 65. So we have a 65. And then we're going to do that for all our letters. So a lowercase u, that's way over here on this page, looks like a 117. And I don't have anything handy, my script for the video. Anytime you hear me say the word script in these videos, I'm referring to a stack of Post-it notes that I might not even look at. Since it covers the whole page, it's not a bad idea to have a piece of paper or something that you can make sure everything lines up clearly. There's a bunch of these on homework. Now, a lowercase g, 103. We already found a lowercase u, so that's 117. And T is one letter before U in the alphabet, so we could do it that way. If you want to do a counting thing, and if you're going to do a lot of this stuff, that's probably what you're going to do. Find a letter, have something at the beginning, middle, and end of the alphabet. So we know what U is. T is right before that, so T must be 116. And S is right before T, so that has to be 115. Or check the chart. Either way works. So yeah, 115 is a lowercase s, 116 is a lowercase t. But they're in order. The letters are in order, so if you find a couple scattered around the alphabet, you can count it out pretty quickly too. So now we just need all of these in binary. And it's ASCII, so we need 8 bits for each one. So a 65, we don't have any 128s. You cut that in half, 128, the next one's 64. Well, I have a 64 in there. That leaves us with just one, so we don't have any 32s. Don't have any 16s, just cutting it in half. Don't have any 8s, any 4s, any 2s, but we do still have a 1. So we go from our letter to the decimal value and then convert that into the binary. So 117 is the next one. So we don't have any 128s. We'll have a 64, and probably not a bad idea to have a calculator in hand and just do the subtraction unless you want to do it in your head. 117 minus 64, 53. So we have 53 left. So we'll have a 32. Minus 32 is 21. We'll have a 16. Minus 16 leaves us 5. So we don't have any 8s. We will have a 4. Minus 4 leaves us 1. So no 2s and a 1. So we can do it that way. Or like I showed at the end of the previous video, both of these calculators have the conversion on it. Casio's a much higher quality than the Dollar Tree one, but most of us are on tight budgets. I think I paid $12 for that at Walmart, so not super expensive, but still $1 is a whole lot cheaper. So then we can just do those conversions. So to save some time here, I'm just going to go ahead and do it this way. Well, we already have this number, right? And we could follow the pattern and find the 2 right before it really easily just by shuffling the bits around, but we can just punch it in the calculator and convert it. So 103, and on these Dollar Tree ones, the decimal to binary is above the division symbol, so I'll push shift division and get 1100111. Which, yeah, I made the point at the end of the last one. Please do a couple of those by hand just to get the practice, reinforce those skills. But this is IT. We're taking, we're IT, we're technology people. We should be using the technology. So which one did I just do? 103. So now I can reset that to decimal. And 117, you can just copy it from right here. I can check what I did because I was talking when I did that. And mistakes happen when just writing, so happen way more often when talking and writing at the same time. 1110101. Okay, yeah. I have to get that wrote down correctly. So then 115. Switch that back to decimal. 115. Convert to binary. 1110011. And finally here, 116. Shift division gives 110100. 1, 2, 3, 4, 5, 6, 7. And, well, the calculator abbreviated things, right? If there's calculators are set up so there's a 0 beforehand, we don't write that. So on all these I just did in the calculator, it only gave me 7 bits. Because every single one of those is less than 128. Or less than 127, so it only gave me, so our 128 column didn't show up. So make sure on your homework that if you use a calculator that truncates that first 0, that truncates zeros to the left-hand side, that you put it back in. So make sure you have 8 bits. That's what I was trying to say there. Because the calculator will get rid of those extra, get rid of zeros, not show zeros it doesn't need to show. So that is how we would represent the word August in binary. So I'll erase the board and we'll do an example going the other way, and that'll be it for these binary lectures. Quite a bit here, but the rest of the semester is all examples on putting code together. So this is the rest of the content stuff will work into examples where we're writing programs. So one more example will finish up the long content type examples. And then the rest of the semester we'll be doing examples of putting programs together to cover the content. All right, here we go. Whew, that's a mess, right? Don't let it overwhelm you. Right? We only have 2 symbols, so any data we store in binary is going to be have lots of those 2 symbols. So don't let it overwhelm you. Just take it a little piece at a time. We know we're in ASCII code. If you're working in binary, you're going to know where you're at. You're going to know what it is. So we know we're in ASCII code. So the first step is to split this up into into bytes, chunks of 8 bits each. So I'm going to grab one of the color chunks, the green one here, and just split this up into bytes. 1, 2, 3, 4, 5, 6, 7, 8. So there's the first byte. 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8. So, look like that's a big long string. There's only 3 symbols there. So, don't let it overwhelm you. First thing you want to do is split it up into those small chunks that you can deal with. This next one, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So again, well, that string looked longer, but there's still only 3 symbols there. That's because I wasn't very even when I wrote my 1s and 0s. 1, 2, 3, 4, 5, 6, 7, 8. All right, so now we can see how many symbols we have. 6, 7, 8. We have 8 symbols. So we just want to split it up into pieces. Don't let it overwhelm you. Just take it a little piece at a time. Do you remember we have that to get from binary into decimal? We can use the hex, or go through them one at a time. I'll do one with just the binary to decimal. Then I'll do one with that binary to hex to decimal. So make sure you're practicing this just to reinforce the skills. And then on the rest of these, I'm going to use the calculator again. Just to speed up the example. But while you're doing this, you want to practice these skills. Help reinforce the knowledge. Which, just to be on the safe side, I'm going to go ahead and have the calculator in my hand while I add these up. So what do we have? We got binary to decimal. So we don't have any 128s. Then we have a 64. So I'll just add them up with the calculator. So 64 plus, don't have any 32s. The next one's a 16. So 64 plus 16 plus no 8s, no 4s, plus 2 plus 1. So our first symbol, our first byte is 83. So then we can just go over to the chart, grab our chart out of the textbook, and find number 83 on here. It looks like that's going to be a capital S. And you're probably going to figure out what this says way before we get to the end. But the next one, we'll do this one the other way. Remember, we have that way we can go hexadecimal. We have hexadecimal because that makes the conversions between binary and decimal easier. So if we split that byte in half, we can take each 4-bit chunk by itself. So 0, 1 power, so that's a 4. which is still a 4 because it's a digit. It's not past 10, so it's not one of our letters in hexadecimal. Then 0, oh, another 4. So here we have 4 times 16 plus 4 times 1. So if you're not sure what that is, just punch it in the calculator. 4 times 16 gives us 64. So we have 64 plus a 4, so a 68. And once again, just go over to our chart, find 68 on here. There it is. Looks like 68 is a capital D. And in the past, couple semesters back, I used the same example, and at this point, somebody in the class guessed what it was. So now I'm just going to do the rest of these with the calculator, just to save time in the example, because we've already gone over that conversion process, but you might want to practice it just to reinforce the skills. So our next one here, I need to set the calculator to binary mode, so push shift and the decimal, because along with conversion, that's actually a mode for the calculator. So now in the calculator, you'll see I can't type any of these numbers. I can only type 1s and 0s. So it's in binary mode. So I'll enter this. 0, 1, 0, 0, 0, 1, 0, 1. Then do shift, the plus sign converts to decimals, and that's saying 69. Which we can check the chart, or the previous one was a 68. So 68 was a D. The next letter, whether after capital D, is going to be a capital E. And then, yeah, we can just continue this. So put the calculator back in binary mode. Then 0, 1, 0, 1, 0, 1, 1, 0. Convert that to decimal. I got an 86. Which we could count from the S. Or come over to the chart again. Find 86 on the chart. There it is. Looks like a capital V. As in vacation. So our next one, well, there's only 1, 0. There's only 1, 1, and the rest of them are zeros. We can probably do that one by hand quicker than we can punch it in the calculator, right? Because there's only one power of 2 in there. So which power of 2 is it? There's 0, 1, 2, 3, 4, 5. So all we have is something in the 2 to the 5th column, which is a 32. Which I mentioned that one specifically earlier, but again, we can go grab the chart, look up 32 on the chart, and you'll notice on our chart in our textbook, 32 is empty. So, as humans, we know what the empty character means. The computer does not. It's just another symbol. It's just ASCII character 32. Has no idea what that is. I wrote it within the escape sequence earlier. I'll just continue that because that makes it easier to see there. But our space. So we have SDEV space, and yeah, by now you've surely guessed what the last 3 are, but let's go ahead and go through the process anyway. Put the calculator back in binary mode. Then 0, 0, 1, 1, 0, 0, 0, 1. Convert to decimal and get a 49. Come check the chart. 49 is going to be on our first page here. A 49 is the digit 1. So SDEV space 1. The next one, go to binary mode, 1, 1, 0, 0, 1, 0. And decimal is 50. We're going to check the chart, or just notice that it's the next one after our digit 1, the digit for 1, the next symbol after the digit 1, and we know that's going to be a 2. And then we can do this once again. Well, I'll do x, because then we have the 0 here, so plus 0, so all we really need is this x value, which 1, 1, that's a 3. 3 times 16, you can punch in the calculator, that's going to be 48, which ASCII 48, well, we can check the chart, or just recognize that it is one symbol before our symbol for the digit number 1. And we know what number comes before 1, so that's the symbol 0. So there's our message. SDEV space 120. And this is why the space is so important, because the computer has no idea what that is. We take it for granted. Our code in the book just leaves that spot blank, and we know what they're talking about. To the computer, it's just ASCII code number 32. ASCII character 32. It has no idea what it means. So just a short example there. There's a few of those in your homework, going from ASCII to binary and then going from binary to ASCII. And don't let the long string of binary intimidate you. You know, for this week's homework, and anytime you work in binary, you know what it's going to be. For this week's homework, when you have long strings of binary, it's either going to be a number or it's going to be ASCII. And, well, it's in a question on homework, so it's going to say in the question what you have. So anytime you're doing this, you know what you have. So the really long strings, you're going to know it's ASCII code, which means 8 bits each, 1 byte for each symbol. So just split it up into the bytes and take them 1 byte at a time. And yeah, it'll take a little while, and then when I grade it, I'm just going to run it through a converter. Well, obviously this one I can just read, but the ones where you go from ASCII into binary, I'm just going to take the binary you submit and run it through a converter and see if it prints out the right string when I grade those. Which if it doesn't, I'll put what the converter spit out into the comments so you can figure out what went wrong along the way. If that happens, hopefully nobody's going to have any trouble with that. Just take it a little piece at a time. Get that big long string of binary. Don't let it intimidate you. Just break it up into little pieces that you know it is and deal with it one piece at a time.